Meropenem is a broad-spectrum carbapenem antibiotic, vital in combating multi-drug-resistant bacterial infections, particularly gram-negative bacteria. However, the rising resistance to these antibiotics poses a significant threat to public health by limiting treatment options and increase our risk of severe infections and mortality. To address this concern, polymeric nanoparticles are being explored. These biocompatible nanostructures can carry antimicrobial agents, enhance drug delivery, and bacterial targeting. They can efficiently encapsulate a high drug payload, safeguard antibiotics degradation, and offers a controlled release profiles. In this study, we used the nanoprecipitation method to synthesize polylactic glycolic acid polymeric nanoparticles for encapsulating meropenem, where the meropenem solution was added dropwise to the polymeric solution to form an emulsion, and then was sonicated to reduce the droplet size. Next, the organic solvent were evaporated and the nanoparticles were washed to remove any residual solvent or reagent. The resulting nanoparticles were size and morphology characterized by dynamic light scattering and scanning electron microscopy. The drug encapsulation efficiency and release kinetics were analyzed by UV spectroscopy, and subsequently we test the nanoparticles' stability under bacterial growth conditions with culture media and temperature. We assess the nanoparticles' functionality for meropenem delivery in Klebsiella pneumoniae and Acinetobacter baumannii meropenem resistance and sensitive clinical strains with minimal inhibitory concentration microdilution method. In the results, nanoparticles in SEM analysis show an approximately size of 102 nanometers, while UVB spectroscopy exhibit a 76 encapsulation efficiency of meropenem. Their drug cumulative delivery capacity was 68 and 85% at 8 and 144 hours respectively. The tests under bacterial culture conditions in two types of culture media demonstrate a significant increase of nanoparticle size in brain hair infusion broth at 24 and 48 hours, while in Miller-Hinton broth, the nanoparticles conserve its size and morphology. A predictable result based on the high concentration of certain compounds in the BHI media that can interact with the nanoparticles and increase their size. The bars graphic showed growth inhibition results for the strains at different concentrations of nanoparticles. For Acinetobacter baumannii, we obtained MIC values of 1 and 160 micrograms per milliliter for susceptible and resistant strains respectively, while the corresponding MIC for Klebsiella pneumoniae were 1 and 90 micrograms per milliliter, dry weight measure concentration. Since the concentration of encapsulated meropenem within the nanoparticles correlates with the mixed values obtained using meropenem alone for both strains, our findings confirm a preserved and enhanced antibiotic activity of meropenem after 16 hours of exposure. These results are according to other studies in bacterial strains using another antibiotics and carbapenems to minimize the antibiotic-resistant pattern. In essence, meropenem PLGA nanoparticles demonstrate effective antimicrobial activity against both strains, thus highlighting their potential biomedical application owing to their encapsulation efficiency, preserved antibiotic structure, and reliable delivery capability. However, future investigations are necessary to explore the effect of particle size, surface charge, and material composition of these nanoparticles to assess the antibacterial activity.